All right, let's tackle a few homework problems related to discrete dynamical systems. So let's start with number 2. This one says, suppose the eigenvalues of a 3 by 3 matrix A are 3 and 4/5 and 3/5. And they don't even tell you what the matrix A is. But we do know the eigenvalues and the eigenvectors. And we know our starting vector. So it says, find the solution for the general equation that moves you from one step to the next for this particular x0, and describe what happens over the long run. So we're, of course, ultimately wanting to be able to do things like a times x and a to a very high power times x. And then look at what happens as k goes to infinity for our particular x0. And we know that that's going to be a lot easier for us to analyze if we break this x0 down into combinations of these three eigenvectors. So that's the first thing for us to do, is just to say -2, -5, 3 can be written as some combination of 1, 0, -3 plus some multiple of 2, 1, -5 plus some multiple of -3, -3, 7. Okay, so there's my starting vector, which I'm going to break down into my three eigenvectors. I'll call them V1, V2, and V3. So I just need to solve this system, which is just an augmented 3 by 4 row reduce, which I already did. I put the -2, -5, -3 on the right because I always like my equal signs on the right. But anyway, the solution is 2 of the first vector, 1 of the second, and 2 of the third. So 2 of that, 1 of that, and 2 of that. I'll just check a couple entries to make sure. So on the top, let's see, that'd be 2, plus 2 is 4, minus 6 is -2. And 0, 1, minus 6, negative. Yeah, it looks like it's working fine. Okay. So anytime I multiply x0 by a, and therefore multiplying each of the eigenvectors by a, that's the same thing as multiplying by their appropriate eigenvalues. So a many times, well actually here, let's undo that. First of all, just doing a once is the same as shoving in a times 3 right there. The second one was 4/5 right there, and the third one was 3/5 right there. And then, of course, as you do a to higher and higher powers, this is the same thing as doing these to higher and higher powers. So this really is the transition. This will give you xk to any power for this starting value. And describe what happens as k goes to infinity. So as k gets bigger and bigger and bigger and bigger, 4/5 to the k gets smaller and smaller and smaller and approaches 0. And so does 3/5 to the k. So you can say as k approaches infinity, these two terms drop out, and x to the k approaches 2 times 3 to the k times 1, 0, -3. So as k approaches infinity, as time goes on, first of all, population, or whatever this is, sectors of an economy or populations or whatever, definitely grows. It multiplies by 3 every step, basically. But whatever this middle term is, vanishes. And you get a ratio of 1 of the first thing to every -3 of the second thing. So This probably isn't a population, but it's something that can take on positive and negative values. So it ends up with this ratio between thing 1 and thing 3 out of these three things. And that ratio triples every transition over the long run. Okay, that's number 2. Let's move on to another example. Okay, so this is number 4 from your homework, which actually refers back to example 1 from the text, so I pasted that in as well. So 4 says, determine the evolution of the dynamical system in example 1, where the predation parameter P is 0.125. So this is a predator-prey system about owls and wood rats, and the predation parameter basically says how good of a hunter is the owl. So right here we've set the predation parameter to be 0.125. I think in example 1 it's actually set to be something different, so they're changing it here. As time passes, what happens to the sizes of the owl and the wood rat populations? And they tell you, they kind of give it away. They tell you the system tends toward what is sometimes called an unstable equilibrium, so we'll find out what that means. And then what do you think might happen to the system if some aspect of the model, like the birth rate of the wood rats or the predation rate of the owls, were to change slightly? Okay, so let's take a look at what we've got here. This is the transition matrix. It's not exactly in matrix form, but let's put it in 0.5, 0.4, negative P is the constant there, and 1.1 times owl and rat populations. I don't like that. Oh, that looks like a 0. It still looks like a 0. Okay, we'll go with it. If you care about the setup here, this is saying owls, the next round of owls, half the owls that we currently have would sort of reproduce on their own. And then, depending on how many rats there are, that also contributes to the growth of the owl population. So the more rats, that contributes like 40% to the growth of the owls. The rat population, on the other hand, just the rats, 1.1, so they reproduce on their own, right? A lot faster than the owls do. Each owl produces like half of another owl on its own, and the rats produce 1.1, so their population grows a lot faster. But they are reduced by the size of the owl population with this P, this predation. Okay, anyway, that's the setup. We don't really need to know that, but we do need to figure out, in this example, if the predation parameter is 0.125. So that's what we're looking at. 0.5, 0.4, negative 0.125, and 1.1. And we need to set up we need to find out what happens as time goes on. So eventually we need that growth equation that comes from the eigenvalues and the eigenvectors. So let's find those things. We need the eigenvalues. Let's see, 0.4 times 0.125. 0.4 times 0.125 is 0.05. And multiply this out, so we get lambda squared minus 1.6 lambda 0.5 times 1.1 is 0.55 plus 0.05 is 0.6. I believe I'd better check my arithmetic there. Okay, yep. All right, now we need to either factor this quadratic or plug it into the quadratic formula. In this case, it's not too hard to actually factor. Oops. Because we're looking for things that multiply to 0.6 and add to negative 1.6. So lambda minus 1 and lambda minus 0.6 multiply to 0.6, add negative 1.6. So our eigenvalues here are 1 and 0.6. Okay, so now we need the eigenvectors that go with each one of those. So let's see, for 1, so I'll do lambda equals 1, so subtract 1. So negative 0.5, 0.4, 0. And the other row should have the same information, so I really don't even need to write it out, but let's just check to make sure. So negative 0.125, 1.1 minus 1 is 0.1, 0, and yeah, if you multiply the bottom row by 4, you get the top row. So they're multiples of each other. So we get some sort of equation. Let's see, I guess I'll go down here. We get negative 0.5 x1 plus 0.4 x2 equals 0. 0.4, 0.5. Move that over, so x1 equals 4/5, x2, and x2 equals x2. So the eigenvector is any multiple of 4/5, 1. And as usual, I kind of like to see whole numbers, so let's choose x2 to be 5, so we get 4, 5 as the eigenvector for the eigenvalue of 1. So same thing with 0.6. I'll go a little bit faster maybe on this one. We subtract 0.6. My face needs to move. So subtracting 0.6, we get negative 0.1, 0.4, 0, and I'm not even going to bother with the second row because I know it's going to be a multiple. And I'm going to scoot through this a little bit faster and say if we do 4 of the first one and 1 of the second one, that will 0 out. So I'll just do 4, 1 right there. So that's enough for us to sort of write out the long-term behavior. We don't even have a starting value for owls and wood rats, but I know that over the long run, x sub k is going to be four, 5 had an eigenvalue of 1, so 1 to the k plus 4, 1. That had an eigenvalue of 0.6, so 0.6 to the k. The only unknown here really is that starting value. So there's going to be some sort of a and b there that were the values we needed to create the starting O and R. But whatever those are, I can still tell that this term right here is going to go to 0, right? Because 0.6 to the k, that approaches 0, so that whole term drops out. So our unstable equilibrium that they were talking about here is saying the ratio will have equilibrium. It'll always be a ratio of 4, what's the first thing? Owls. 4 owls to 5 rats. And if you look back at the units, this is owls versus thousands of rats. So 4 owls versus 5,000 rats. And it doesn't grow or decline, right? The eigenvalue is the same. So whatever this 4-5 ratio is, based on A, whatever that A value is, whatever that 4 owls to 5,000 rats times 2 or times 10 or whatever A is, stays. And I think you can imagine that if some aspect of the model got tweaked just slightly, then this eigenvalue wouldn't be 1 anymore. If you tweak it a little bit, maybe the eigenvalue is 1.1 and both populations grow. That would probably come if you tweaked it by increasing the reproductive rate of the rats. Or maybe it goes down to like 0.9 if you tweak it, maybe if the predation is a little bit higher and the owls are a little bit better hunters, in which case both populations actually decline. The owls are eating better in the short term, but they're killing their food source faster than it can reproduce, and so both decline. But they do it at the same rate, at this 4 to 5,000 ratio. Okay, so that's example 4. Let's jump on to one more example and take a look at problem 12. So we're moving away from applications. There's no wood rats here. But they just want you to analyze this thing and classify the origin as either an attractor or a repeller or a saddle point. That's the technical name for that one eigenvalue being bigger than 1 and the other eigenvalue being less than 1. So you sort of whoosh around these. I don't know, it doesn't exactly look like a saddle to me, but maybe it does to you. Where was that picture? Was that this? Nope. Yeah, that's a saddle point. So I don't know, are you sitting on a saddle there? And doesn't look very comfortable. Anyway, it's called a saddle point. So we basically need to do the same thing here. We need to find the eigenvalues and eigenvectors, and that will sort of tell us whether both things shoot away no matter where you start, or both things get drawn in, or if there's a saddle point. So let's tackle eigenvalues and eigenvectors. And then they also want to know the direction of greatest attraction and or repulsion. And by repulsion, they don't mean the repulsive food that you've been eating, cooking for yourself. They just mean those eigenvectors. Okay, so eigenvalues, here we go. Actually, I don't even need to write the minus lambda on the main diagonal. Let's just jump straight to the characteristic equation. So that'd be 0.5 minus lambda. 1.4 minus lambda plus 0.3 times 0.6 is 0.18 equals 0, and multiplying things out to get lambda squared plus 1.9 lambda plus, let's see, that's 0.7, 0.88 equals 0. And again, you either factor this if you can see how it factors, or you use the quadratic formula. It turns out this factors into lambda minus 1.1 and lambda minus 0.8. So we get eigenvalues of 1.1 and 0.8. And by the way, we already know the origin is not an attractor or a repeller. That's a saddle point, because one of the eigenvalues is bigger than 1, the other one is smaller than 1. And if that's all they'd asked in this problem, we'd be done. However, we also need the direction of greatest attraction or repulsion. And again, to get this picture back, oh, I didn't write the eigenvalues down on this one. But the green here was an eigenvalue that was less than 1. So that was drawing it inward. And the purple was a greater than 1, and that was pushing it outward. So for this one, the direction of greatest repulsion is right along this purple. That's repelling the hardest away from the origin. And the direction of greatest attraction toward the origin is this green. So the direction of greatest repulsion here will be the eigenvector. Yeah, let's get right back on the right layer. Will be the eigenvector that goes with this eigenvalue. That is the fastest trip away from the origin, going at 10% every time, 1.1. Anything else is going to be made up of a combination of 1.1 and 0.8, so it won't go away from the origin as fast. And the direction of greatest attraction to the origin would be this eigenvector. If you're just straight on the 0.8 eigenvector, then you'll get 80%, 80%. You'll get 20% closer every time. Again, anything else will be made up partially of this one that's repelling. It'll be a push-pull, and you won't get there as fast. So we do need to find the eigenvectors that go with these two eigenvalues as the short story. So if we do 1.1, actually, you know what? You guys are good at finding eigenvectors at this point, so I'm going to cheat a little bit. So the eigenvector for 1.1 happens to be 1, 1. And the eigenvector for 0.8 happens to be 2, 1. So the direction of greatest repulsion is like the 45-degree angle is 1, 1, right? Is that direction. And that's the fastest highway out of town. And the fastest highway into town, these are all one-way highways, is if you go 2 over and 1 up. So I guess is this direction is the greatest attraction. Okay, that is it. This is the last video for linear algebra for Math 204. Tackle that 5.6 homework. And then you've got both the Chapter 5 test to do and the final project that's cumulative for the whole course. So you got lots of projects to keep you busy. If you have questions on anything, as always, just let me know.